urgent, intense tone. When a 9.8 CVSS vulnerability drops without warning, security teams abandon everything else to contain the blast radius. In the case of CVE-2026-20253, the target was Splunk Enterprise. The threat was an unauthenticated remote code execution, or RCE, vulnerability. The immediate industry reaction is entirely predictable. SOC and DevOps teams work frantically through the night to push patches, restart servers, and close the open vulnerability. To understand the specific danger here, we have to look at what an unauthenticated RCE actually permits. It allows an external attacker to execute arbitrary commands on a target system without ever needing a valid password or user credentials. Once the patch is successfully applied, the dominant operational assumption takes over. The vulnerability scanner shows green, the alerts stop, and teams assume the network is secure. The problem with this logic is that patching a server only prevents future exploitation. It has absolutely nothing to address what the attacker actually did during the hours or days the window was wide open. Rushing to patch creates a dangerous operational blind spot. It tricks incident response teams into concluding the threat is neutralized, causing them to ignore the actual damage sitting entirely undetected in the dark. To find that damage, we have to shift our focus away from the compromised application layer itself and examine the forensic evidence it houses, the system logs. An audit trail serves a singular purpose in cybersecurity. It provides the only mathematical proof of exactly which files an attacker touched, what data they stole, and which configurations they altered. This introduces the SIEM Integrity Paradox. Your security information and event management platform is the vault designed to guard those logs. When the vault itself is compromised, the logs inside become inherently suspect. This leads to an incredibly uncomfortable question for security directors. How can a team mathematically prove an attacker didn't alter the logs before the patch was applied? Analysts look at their dashboards and assume they are seeing a chronological, factual reality. The objective reality is that once an attacker gains execution rights, the timeline presented by those dashboards cannot be trusted. Losing log integrity creates cascading failures across an organization. Security teams cannot accurately report the scope of a breach to regulators, quantify the exposure of customer data, or guarantee that the attacker has been entirely evicted from the network. An unauthenticated RCE on a SIEM invalidates the forensic truth of the attack by compromising the very system used to record it. Look at this traditional SIEM architecture. Systems like Splunk are built as a monolith. All core functions, ingestion, the analytics engine, and database storage live under one operational roof. That solid enclosing line is the trust boundary, placing them into a single security context. In normal operation, the data flow is highly efficient. Raw data enters through ingestion, gets processed and indexed by the analytics engine, and is written directly into storage. Vendors rely on this design because it offers high speed and tight integration, maximizing query performance for analysts hunting for threats. However, prioritizing speed over isolation creates a structural danger, a total lack of internal compartmentalization. In a monolithic system, the application layer, the analytics engine, inherently possesses broad read and write privileges over the underlying storage layer. This lack of isolation is not a bug. The application must possess these high-level privileges to function, organize indexes, and manage data correctly on behalf of the user. The engineering implication is severe. Any entity that manages to control the application layer automatically inherits those exact same read and write privileges over the database. Because the analytics engine and log storage exist within the exact same trust boundary, compromising the application guarantees the compromise of the entire historical record. Let's apply the CVE-2026-20253 vulnerability to this monolithic structure. The attacker bypasses authentication entirely. They gain arbitrary execution rights directly on the analytics engine, securing a firm foothold inside the trust boundary. The attacker executes an immediate pivot. Leveraging the application's native read and write permissions, they burrow straight down into the log database. First, they identify and selectively erase the initial intrusion alerts from the database, silencing the alarms they tripped on the way in. Next, they fabricate fake logs and inject them into the system, creating a heavy diversion designed to send incident responders on a time-wasting wild goose chase. Finally, they delete the logs that recorded the log manipulation itself. They wipe their footprints entirely clean. The security team arrives to review the dashboard. They see a perfectly clean timeline showing normal activity, completely masking the total system compromise. A newly patched application sitting on top of heavily manipulated logs generates a false sense of security. The attacker has successfully rewritten history. Diagnosing a monolithic failure is only the first step. The goal is to engineer a resilient, mathematically sound alternative from foundational principles. The ultimate engineering objective is absolute isolation. A remote code execution in the analytics tier must be physically unable to impact the storage tier. We achieve this through decoupling, the direct structural antidote to the shared trust boundary flaw. This diagram shows the first step of decoupling, physically separating the log ingestion pipeline from the analytics engine. We then establish a worm-compliant cloud storage layer. Write once, read many is the foundation for maintaining data fidelity. The write once mechanic is strictly enforced at the storage level. Once a log is written to the bucket, it cannot be altered or deleted by any system process, regardless of privileges. The read many mechanic allows external systems to analyze the data freely, pulling insights without ever risking modification or corruption to the source files. By physically removing the storage layer from the application's control, the core structural dependency that made the monolith vulnerable is entirely eliminated. This brings us to how Sasquatch Labs specifically implements this decoupled architecture. In this model, the Sasquatch query engine is completely isolated from and hovers independently above the storage tier. The connection protocol is rigid. The query engine operates with strictly scoped read-only access. It can see the data, but it cannot touch it. Let's run the exact CVE-2026-20253 attack scenario again, this time against the decoupled Sasquatch architecture. Even if the query engine is completely compromised via an RCE, the attacker's privileges abruptly stop at the read-only barrier. The attacker is effectively trapped. They can view the historical data flowing upward, but they are mathematically prevented from rewriting the immutable audit trail below. Architectural separation is the only method to guarantee that forensic truth survives an application layer breach. When the next 9.8 CVSS vulnerability hits, your team will scramble to survive it. The outcome will be entirely dictated by the architecture you chose today. The monolith leaves you with untrustworthy data. Decoupling leaves your evidence pristine. Guaranteed data fidelity yields specific operational advantages: faster incident response, undeniable compliance reporting, and mathematically proven attacker eviction. Waiting for the next zero-day vulnerability to test your log integrity is a critical failure of engineering foresight. Stop trusting legacy systems to guard their own evidence. Start verifying your security with an immutable architecture. Go to sasquatchlabs.io/demo to spin up a live engineering demo. Run your own traffic analysis against a fully decoupled stack. True security resilience is found in engineering an audit trail that outlives the breach itself.